So what we're looking at here is the effect that adding heat, and we're adding heat in this direction, okay, has on water's temperature and other things, actually, because really the temperature, notice, there's places where it goes up and where it doesn't go up. All right, so we're going to start with ice. We're going to go all the way up to steam and look at those effects, okay, on a graph. Now, temperature, it's really important that you understand that temperature is not the same thing as heat, okay? Temperature, to a scientist, is a measure, or a relative measure to be more correct. Relative meaning it's dependent on something else, okay? It's comparing one thing to another. A relative measure of the average random well, let's say motion. We should say velocity, I suppose. You know the difference between motion and velocity? Do you? No? I see deer in the headlights look. Okay? Yeah, I'm not sure. All right. Let's just put motion in here. Motion is really not as accurate as I'd like to be, but just for right now, we'll call it motion. Okay? Or speed, I guess you could put in there. Okay, but speed and velocity are really two different things. Average random motion of particles in a substance. Or let's say a material, because it could be something other than a substance. Substance is specific in chemistry. So let's say a material. Okay? All right. And what that means is that the particles, now we're talking particles, we're talking about structural particles in a material. We're talking about the atoms or the molecules or the electrons or other things. Okay? Really, really tiny particles here. Everybody got that? And they have to be moving randomly. That means they all can't be moving in the same direction. If I have all the particles in a substance or a material moving very fast in the same direction, they could have zero temperature. Okay, no temperature at all. That really won't happen, but theoretically speaking, that's what we're talking about. It has to be random motion. All right. So they're either wiggling really fast or they're actually moving around like a gas is moving around faster. And the faster they wiggle or move, the motion or velocity, the higher the temperature. You got that? All right. So that's different from heat. Okay. Heat is energy. It's not the motion of particles. Okay. Heat is something else. It's actually energy. It's the ability to do. Well, let me define that. Let's put that down here. Heat is the ability to do work. And we can take heat and drive a steam engine. Okay? So if it can do the work of driving a steam engine, it's a form of energy. Okay? Actually, energy is the ability to work. Heat is one form of energy. Okay? Heat affects temperature. Okay, heat affects temperature. Because when you transfer heat from one place to the other, you cause the structural particles to increase that motion. Okay? So yesterday we did a demonstration called the whoosh bottle, and the heat inside the bottle, the heat was transferred from the bonds in the molecules to the particles of gases inside the whoosh bottle. Okay? And so we got more rapidly moving particles inside that whoosh bottle. And then I sealed up the top and it kind of shrunk down. You can see it shrinking down because the heat then was transferred from those gas particles inside the whoosh bottle to outside. Okay? Got all that? All right. Now we're going to go back to our original graph here. We're going to look at what happens as we add heat to a substance. Now, you could also take heat away and simply go in the other direction. So we're looking at what's happening as we add heat. So this is what's happening as heat is added. So heat is increasing. And we could say is added. All right, if you want to, just to further clarify what it is. All right. And we have degrees C and 100 degrees C over here. And for some reason, this is out of place. That degree C should actually be right here. And the 100 degrees should be right here on this line. Okay? I don't know how that happened. Please mark that. So this is the actual temperature. And so if we were labeling this properly, we'd show what units of measurement we're going to use. Degrees C. Now since down here heat is measured in joules, we could say this is in joules. Okay? Now the amount of heat added will depend on the amount of water. We're not going to be getting that specific on this graph. Okay? Alright. So we're going to first look down here. Down here we're talking about when water is ice. So it's below zero. We got regular room temperature. Alright, we don't have room pressure. We don't have low pressure or high pressure. And so below 0 degrees C, if you get ice below 0 degrees C, it must be frozen. Okay, now there are ways not to have that happen, but typically. Alright? So this is where we have ice. Got ice down here. So if I have ice that's way below 0 degrees C, okay, and you can cool ice way down below 0 C, okay, any solid can be made hot or cold, or hotter than cold, before it starts to melt. When I add this energy in joules, we can actually calculate. There's actually an actual equation that defines how adding the heat affects the temperature. So there are a couple things you need to know about that. We got T means temperature. That's our symbol for temperature. Temperature, T, yeah. And delta is the symbol we're going to use for change. And then we've got C subscript P, capital C subscript P. And that stands for what's called the specific heat or heat capacity. Let's call it heat capacity of a substance. Now it's really important you understand that every substance has a different heat capacity. Okay, just because water's heat capacity is, and when it's liquid, 4.18 joules per degree, per gram. Okay, it doesn't mean that everything has that same heat capacity. Okay, every substance has a different heat capacity, and the physical state of every substance has a different heat capacity. So solid or ice, the solid form of water, has a different heat capacity than the liquid form we'll have over here. The liquid form or the gaseous form. Okay? All right, but the relationship between the amount of heat energy and the temperature is defined by this equation right here. It's Q, which is how we represent heat energy. Q means heat energy. Equals the mass. So the mass of the water matters times that specific heat that has to be calculated, figured out, times the change in temperature. Okay? So that's how we calculate. If we know what the change in temperature is, we can figure out how much heat was added. If we also know the mass, and we look up the heat capacity. Yeah. However you want to write the multiplication is fine, or you can use dots instead of time signs. Okay? Dots and time signs at this level mean the same thing. But there are times later on in like high-level math in college where you're going to find out that those actually mean something different. Okay, but at this level, at this point in time, you're not in the stuff where you have to differentiate between those. So a lot of times you'll see dots instead of that. Okay? So that's the relationship. Heat energy times the mass of the water or any substance, really. This actually works for anything that is changing temperature. Anything that's changing temperature has this equation. The difference is the CP. Every substance has a different CP, and every physical state of every substance has a different CP, which is the heat capacity. Okay? Got it? We're just looking at water as an example, because water is used very, very commonly. In fact, the way we figure out the specific heat of other things is we start with the CP of water, and we figure out how it changes the temperature of water when it's next to it. So we put stuff in water to figure out what the CP is. That make sense? All right. And you use what's called a bomb calorimeter for that. It doesn't really blow up. Okay? There's a reason why we call it a bomb calorimeter. All right. Now notice, as I keep adding heat down here, the temperature stops rising after a while. And this is the point where water reaches its melting point. Okay? So if we heat up the ice until we get the ice up to 0 degrees C, the point at which it melts and it freezes, we keep adding energy, there's a period of time or a period where we add more heat that the temperature doesn't change. While it's melting, the temperature doesn't change. Yep.
How does it freeze and melt?
Because we're adding heat energy or taking away heat energy and getting the molecules to lock in place or to break apart from each other. Okay? And during that time, the temperature's not changing. All right? If you were to take a thermometer, and if we had time, we'd do this lab too, and put it in a block of ice, or put the thermometer in water and freeze it around it, okay, you could actually measure all this happening. Okay? So you'd heat it up, and the temperature would rise, but then while the ice is actually melting, the temperature doesn't rise. It stays pretty consistently steady. Once it melts, then the water can increase its temperature, but the ice itself, while it's melting, does not change its temperature. That make sense? Kind of twist your brain around a little bit because you've probably never done that before or thought about it, but that's what happens. Everybody with me? Don't let me leave you in the dust, right? Never leave a man behind. Okay. Well, that means that this equation doesn't work anymore while we're in that transition time where we're changing from solid to liquid. During that transition right there, there's no change in temperature. So that equation no longer works in this region. Okay? While we're melting the ice, we have to have a different equation. Now we're still adding heat energy, so there's still a Q. Okay? Heat is the amount of Q, or the amount of heat energy is changing. We're still looking at what the mass is. But during the time while we're adding energy but the temperature's not rising, while we're melting the ice, all we can measure is, or determine is, that change in enthalpy. Well, there it is again. We used that yesterday in all the math we did. Right? We're doing a combustion equation. That's the change in energy inside the substance. Alright? Now, it's not the bonds here. In this case, we're not breaking any chemical bonds. What we're breaking is what's making those ice molecules stick together. Not the bonds between the hydrogen and oxygen, but what's making the H2O molecule stick to the next one. That's what we're changing. That's the delta H in this case. Got that? So delta H then, or H, is the enthalpy. Still the enthalpy, but it's a different enthalpy in the sense that yesterday we were looking at chemical change, today we're looking at physical change. Yesterday we were looking at what's happening in the bonds between the atoms, today we're looking at what's making those molecules stick together. You got that? All right.